So we've seen a whole bunch of different kinds of algebraic structures now, and I want to kind of go through them and talk about how they're related. So we've studied groups and rings and fields. We also took some little side journeys and talked about abelian groups, which were commutative, and then commutative rings, which were commutative under both addition and multiplication. And then here's another one that we're not going to deal with a whole lot, but it's worth talking about. So something called integral domain is in between rings and fields. So it's a commutative ring. It is a ring, and multiplication is commutative. It has no zero divisors, but it doesn't necessarily have multiplicative inverses. And so the primary example of this is the integers, which is why it's called an integral domain. The integers are an integral domain. They have no commutative ring. They have no zero divisors, but multiplicative inverses aren't necessarily there, so it's not quite a field, right? So if we think through these different structures and how they relate to each other, we've built up this hierarchy of them. So we started out with groups, and most of the groups we worked with were groups under addition, maybe all of them. And so that meant we had this addition operation. It was closed under addition. Addition was associative. We had an additive identity. We had additive inverses. And then we added on to that. So we added on a set that is a subset of groups under addition, are abelian groups under addition. Okay. And abelian groups under addition had all those same properties, but also we needed addition to be commutative there. Okay. And then we added a few more conditions, and we ended up with rings. Okay, so we're abelian groups under addition, but they also had multiplication and a bunch of properties that went along with that. Multiplication had to be associative. We needed a multiplicative identity, and we needed a distributive property. We needed to know how the two, addition and multiplication, interacted with each other. All right, and then from rings, we can add on one more stipulation and get a commutative ring. So commutative rings were rings where the multiplication was commutative. And now the one that we just saw up above, that's a even further requirements on a commutative ring. If we also say we don't want zero divisors, then we're talking about an integral domain. And then if we, in addition, ask for multiplicative inverses, then what we get are fields. So I've used this subset notation kind of sideways here to show a hierarchy. I'm going to draw a little Venn diagram of it if that's a better way for you to think about it also, but first let me give some examples. So let's start with the fields. So fields, the real numbers were a great example of fields, or the rational numbers. And because they're fields, it means they are also all the rest of these things. Okay, so all the rest of those real numbers and rational numbers are groups under addition. They are abelian groups under addition. They are all of those things. For an integral domain, the example we talked about above was integers. Integers are all of those things above. They're integral domains, and everything above. They are not fields. We don't have multiplicative inverses. Okay. I'm going to skip over the commutings. So a commutative ring, we haven't seen a good example of that at this point, and so we won't worry about that one. But let's talk about something that's a ring that's not a commutative ring. That example is our M2R. Set of 2 by 2 matrices formed a ring, which meant they were an abelian group under addition, and they were groups under addition, but they were not commutative rings. They also are not integral domains because they don't have, so they are neither commutative under multiplication, nor are they free of zero divisors. Abelian groups under addition and groups under addition. So a good example of either one of these is the set of even integers. Okay, so I should probably make a little note, my notation there, 2z, that's the set of all even integers. Okay, so that's an abelian group under addition. I can add even integers and I get an even integer. It's not a ring the way we've defined ring because it does not have a multiplicative identity. 1 is not in the set of even integers. All right. So it's good also to have an example. Maybe I'll squeeze it in at the very top, which is none of those things. So the odd integers are none of the following things. So they're not a group under addition, because if I add 2 odd integers, I don't get an odd integer, so it's not closed under addition. All right, so that's a variety of the sets that we've seen and how they fit into this picture. I'm just going to draw one quick Venn diagram so that you have a visual for this also. So the idea here is our groups under addition, that's the big set. So groups under addition. We add on the requirement that it be commutative, and now we get abelian groups under addition. Okay, we add on a new operation, multiplication, and we get the set of rings. We add on that we want multiplication to be commutative, and we get commutative rings. And then we add on the requirement that we have no zero divisors, and we get an integral domain. And then we add on that we want multiplicative inverses, and we get a field. Okay, so those smaller sets, fields is the smallest one, and it's the most rules involved. It's also the one that's nicest to work with. So the real numbers and the rationals, those are great. You can do anything you want with them. The rest of these, you sort of lose bits and pieces of them as you go. All right, so we will keep thinking about these a little bit. We're going to focus mostly on fields from here on out, but the next chapter actually will use fields in a different setting than we've seen so far.